Greetings and welcome to another exciting video. So before I was getting pretty complicated, relatively speaking, with doing the bipolar commutation and the capacitor and timing and all that. So I just want to back up from all that and do something much more simple and sort of show you that anyone can do this. I mean, you can. And so this is going to be a really simple machine, just so that people kind of get the idea. And also, I'll mention some of the strange stuff that goes on with this. So let's just go through each part here, like one by one. We have this rotor that's 4 inches, and it's got a skateboard bearing there in the middle, and on the outside are the magnets, and they're all facing the same direction. See, that's pulling the red. Next one's pulling the red. I'm pretty sure the red is the south pole. I guess that's the south pole there. So this is the north pole. So all of these magnets face the same direction, north facing out. That's called a monopole configuration. So this is a monopole pulse motor. Back here we have a reed switch, which is just 2 strips of wire. In this case, it's in an evacuated glass tube. And, without putting any power on or anything, when I spin it past, you hear the reed going click, 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 click. So every time a magnet goes past the reed switch closes, and there's a connection between the 2 sides of the reed switch. Okay, so far so good. So now, if you have a power supply, we'll use this, and then I might run it on a few little batteries also if we get a chance here. So let's say you take the positive and you put it to the top of the reed switch. The reed switch closes, so now power can flow through to the bottom of the reed switch, comes to this wire, round, and then out here to your negative of your circuit ground. So every time the reed switch goes, power goes into here, and it's on for when you hear the click, and then it turns off. Now, one thing that's a little strange is you can see the reed switches, I'd have to see if it's exactly lined up. It's sort of on this line here, and I have the coil at about a 22-degree angle. Now, you could try and run it in repulsion mode right there, but there's actually another way of running it. I don't know if I can show this or not. When you go between the 2 magnets, come on, let me see if I can show it. I might not be able to. Between, I can't really do it with one hand. Between the 2 north facing out, when they get scrunched together like that, somehow the south pole comes out. It's a weaker south pole. It shows up at about like 22 degrees there. And so you run it at that point. And so that's why it's not lined up 180 degrees off. You want it about 22-degree angle there. And I guess the only other last point I'd make is that if you do this, you want to get the rotor spinning before you turn the power on. I already fried 2 reeds. I'm down to my last one. I've got like a dozen more on order, but they won't be here for a few days. So it's less of an issue with this thin wire, but I was running it through this coil, and that's when I fried them. If you don't have it spinning first, what happens is the first one comes past, and this is on for, like a third of a second. And so the coil initially has a lot of resistance, but then as the magnetic field gets to its peak strength, the only thing stopping the current flow is the direct resistance in the wire. So I mean, this has like 30 ohms, this has like 2. So if these were like half-watt reeds, and if you go past that, it's not very forgiving. So it sees like 0.6 amps for a second, and kapoof. I think this is a 1 amp. I might have one more of those. But maybe if you don't want to worry about that, do it with some thinner gauge wire. I think this is 28 gauge wire. I don't think it's 30, or looks like 28 gauge. And it's sort of very last point there. So the reeds can be a little finicky when you're actually powering the machine through the reed. When I'm using the reed across the Arduino, all it is the Arduino, it's seeing the Arduino 5 volts and it's seeing it across a voltage divider of 2 resistors. So I've never had any problem with the reeds sticking or blowing up or anything like that when I'm doing it through an Arduino. Like this, you got to be careful, and it's harder to go to high voltages. You want the thing spinning a little bit before you start it up. But that's all there is to it. It's just a few magnets, a reed switch, and a coil. And you could, if you wanted, if you don't have a 3D printer, just glue some compact discs together. You can get like 100 of them for like 10 bucks or something. So just super glue some of those together, glue some magnets on the end, and glue a compact disc on top of it, and you have sort of the same thing once you put in your bearing. So why don't we give this a spin and see what happens, and I'll show you what I'm talking about. Now, turn the power on. We're at 5 volts. And away it goes. Now you notice, being at 5 volts here, I'm not even pulling off the inductive spike anywhere. So that inductive spike is like rattling around in the reed switch and things like that. So if you went to higher voltage, you'd want to do that as well. So it would probably make the reed switch behave a little bit better. But this is all you got to do. Let's see how fast we can get it. Okay, it seems to like there a lot better. Now what you also see is as you spin faster, the amp draw goes down. Now, the duty cycle hasn't changed because the magnets are still in the same spot. It's on for the same amount of time, off for the same amount of time. But you have to remember the dynamic resistance of the coil is greatest when it's first starting to establish a magnetic field. And then that resistance goes down as it becomes closer and closer to being fully saturated. So the faster it's going, the greater the dynamic resistance that you're getting from here. So now we're down to drawing 0.05 amps. And it's starting to really chug along. So I don't know if I can show this, and I don't know if I trust the reading. I don't want to bump into the rotor. That's not it. 1195. 1193. So it's spinning at about 1,190. Almost 1,200 RPMs. So not too bad. And if you don't have power supply, and I guess we could do this as well, you can just put like 4 little AA batteries in series and run it off those. That's about 5 volts. Now, if you do that, and I hesitate to mention this because I don't want to be, you've got poop for brains. What are you talking about, man? It's garbage. But if you do that, you can calculate what the milliamp hour capacity of the batteries is. You can get your amp draw off the meter, and what you see is, let's say you're drawing 30 milliamps and you have 1,500 milliamp hour batteries. So after an hour you've used 30 milliamp hours. After 2 hours you've used 60 milliamp hours. So on and so forth. The batteries don't go down as quickly as they should per your milliamp hour reading. They go down, with this I was seeing it was going down at about half as fast as it should. And I think a fairly famous circle in this kind of goofy experimenter community is the Bedini simplified schoolgirl circuit, which is this is it. The only difference is that he put a trigger winding and then ran it through a transistor. But if I recall, in that circuit, he also wasn't pulling off any of the radiant spike, and he helped the elementary schoolgirl put that together for a science fair, and I think it won first place because the batteries weren't going down as quickly as the science teachers were saying they should. And it's not real difficult to see. So I mean, I know it sounds kind of silly, but you can go do it yourself. It's not difficult. So we'll set it up with some batteries. I mean, you'd have to run it for like 6 hours to say, oh yeah, it's going down a little bit too slow. So I'm not going to do that, in this video. But one last thing I'll show here while we have it on this is, and this is something I've showed with like a zero force, and not with the Windows motor because you can't change the spacing, but with the zero force as well. Not to get too far off topic, but I think they're calling the zero force in the conventional world an axial flux motor, as opposed to this would be a radial flux motor. And I saw like Mercedes-Benz or BMW or one of those has come out with an axial flux motor where they're running it like a zero force. But they never do anything with radiant spike, and they always snub it out and whatever. But anyways, so what I'm going to do is move this coil in and watch what happens to the voltage. Okay, so I moved it in there. Now it's going to slow down, but you see I didn't touch anything on the power supply, and then it'll slow down to a much slower speed and it'll go back to 5 volts. And that's because it's running into resistance from this coil, even though it's an air core. So we'll back it out here. So what I'm saying is that there are actually 2 current flows going on, and in a moment we'll look at, just for a brief time, we'll look at Robert Adams' manual on this. And he says the same thing, that not about 2 currents necessarily, but that the batteries don't go down real quick. But you can see there's amps going out this way, but for the voltage to go up, there had to be current going that way. And so that has to do with this coil that's collapsing all the time. Why that leads to the batteries going down more slowly, I don't know. I mean, if I really had to hazard a guess, I'd say, you have the field when it's establishing, and per Faraday's law of induction, that's going to be shooting that current that made the voltage go up. I think that current sees the battery, and so it's just, the resistance is just the charge acceptance in the battery. Then it sees the negative, and that means, oh, we got to shoot more current out, but it hits the impedance of the coil, and so it can't get a lot more current out the other way. That's why I think there's a little bit of an imbalance that leads to the batteries going down more slowly. That's just a guess, but that's my thought. So this is about an 80-page write-up called the Adams Pulsed Motor Generator Manual from there. But you should be able to find it. Released 1993. And it's great. I just finally got around to reading it the other day. But it's just wonderful. So if we kind of scroll down to the end here first, there's Robert Adams from New Zealand. And I guess one thing I would point out is he was a former chairman of the New Zealand Institute of Electrical and Electronics Engineers. So it's not like he's not qualified to be evaluating this. And it is very practical information, a lot of, kind of scope things and whatnot, and a lot of very understandable diagrams and other circuit diagrams, just page after page of them. A lot of stuff, like I was originally looking at, with fun with spinning the 4-inch rotor, how do you put it in series? How do you put it in parallel? What if you put a coil here? He did all that and documented the heck out of it. Here he's just talking about kind of the efficiencies that he's able to get. And in terms of once you have everything dialed in. And, he is saying things, like the briefer the pulse, the better. And so I think a lot of the work I was doing on the breadboard there should carry over. This video is getting longer, so I won't go into what I'm going to do next with the spinning motor. But, well, I'll just mention it real quick. I'm going to, keep the whole cap out of it, but I'm just going to use the Arduino to set the pulse to be very brief. But as long as the magnet's there, it'll just keep pulsing repeated times. So, in other words, when you're spinning at like 1,000 RPMs, it works out to like a 5 millisecond pulse, which is actually pretty slow, especially for that coil that we had. So, I'd like to just set it as a 500 microsecond pulse and just while the magnet is there, have it pulse, say, 10 times. And see what that does in terms of the battery recharge stuff. And then also look at it, when you're pulling off the radiant as well, does the effect on the battery going down more slowly, does that change? So those are really the two things I'm going to do going forward. So, I can't go through all of this in, one video, but so here's, just another graph of it. You see all the north's facing. He's got two drive coils in this setup. And he gives lots of other good ideas of how to increase torque, he's got just loads of these circuits. It's an approachable and an enjoyable read. But, here he's talking about that offset, that 22-degree offset. So I'd highly recommend this. I should have read this years ago. I don't want to gossip. Well, I guess I'm not gossiping. I'm just kind of speculating. But this stuff is pretty much identical to what John Bedini was doing with the simplified schoolgirl circuit and some of the others. He shows in here capturing the radiant also off through a backwards diode, so on and so forth. And so it's like, did they both come up with it independently? And if not, I know this came out in '93, the write-up, but he wrote this after he'd been working on this stuff for, I think, decades. So I kind of wondered, did John get this, all that stuff from him? And I wish someone had pointed this out to me like 5 years ago, because this is just a great resource. And he's even talking about different ways of commutating it. You could use a trigger winding, or you could use a Hall effect sensor. What he does, which is cool, is he actually does mechanical commutation. With a timing wheel with tapered copper, so he can change whether the pulse is a long pulse or put the two strips out there and it's a short pulse, so on and so forth. But I could talk about this for hours and hours, but I think this is enough, and just to say to read it. And let's run it with some batteries and then wrap this up. So here I just have four. They're 1.2 volt rechargeable nickel metal hydrides, and they are sitting at, unloaded that is, 5.38, so it should spin. I will say that I haven't looked at non-rechargeable alkaline batteries, whether those go down slower too, but they're not supposed to be able to recharge at all. So I don't know, but you do see this with nickel metal hydrides. They don't go down as fast as you would expect from the amp draw. So now, exact same as before. The power is coming out. This time I'm just putting it through this to get the milliamps. Boom, boom, coil, boom. So when I connect this to there, then it should spin. So let's get it moving. And hopefully this works. Yeah. Now it's pinning that out for the moment, but it'll go down. So give me a minute we'll see how fast it goes. So it's starting to speed up now. I'll have to hunt around to find a good spot. We're still pinned over 0.05 amps, over 50 milliamps. I'm hoping we'll get that down. I guess this thing was running at like 60, so I don't know, maybe this was the wrong meter. Well, it's running along well now. I picked the wrong amp meter because we're still above 50 milliamps. But you want to use an analog, because if you put a digital, it just goes all over the place. It can't figure out a reading because of the pulses. At least that's what I've seen. So you probably want to use an analog amp meter. So I'll wrap it up here, but that's all there is to it. Just a reed switch or some way to know when a magnet goes past. Power supply, coil, boom, and you're done. Okay, stay healthy, everyone. Bye-bye.